Here's another way to look at this, the same cross that we just went through, but looking at it in a different sort of way. And some students find this more readily accessible than the method that we just looked at. So we had to find that yellow was the big Y allele and that it was dominant to the little y, which was green. And also for the purple and white characteristics, we define that as another allele, big P, giving us purple, and little p, giving us white. This allows us to fill in genotypes for the different individuals. So this means that a pure line that has yellow seeds will be big Y, and also be little p for the white flowers. Over here, we would have little y, and big P. Now, just as an aside, it's important that you carefully distinguish upper and lowercase letters. In fact, I recommend when you're choosing letters to use for allele symbols, it's best to choose something that has a readily distinguishable upper and lowercase. This would mean that the F1 as a dihybrid is now big Y, big P, little p. Another way to put it is when this organism makes gametes, uses meiosis to make gametes, it's going to contribute a big Y and a little p in its gamete set or package. This organism over here is going to provide a little y and a big P. Later on, when we talk about recombination, we're going to be talking about input sets or packets and output sets, so it's useful to think about this now as well. So these two gametes fuse. We could say this is the pollen, this is the ovum, for example, to give us this organism that is now a dihybrid. Now what we can say when this organism is selfed, get myself a little bit more space here. So a self is an F1 times an F1. We can now ask ourselves what sorts of gametes this organism, this dihybrid, can form. Well, it can form a number of different gametes. Now, when it's forming gametes, it's important to remember that it's only going to take one allele of each locus. We're never going to have two Ys in a gamete. We're never going to have two Ps in a gamete. We're talking about this reduction from 2 N cells down to N, one copy of each locus. So it's important that you make sure that you're not inappropriately segregating your alleles. If you work through the different options, you'll see that there are 4 different possibilities for gametes that this organism can form. Okay. Now we can ask ourselves, what's the probability that these different gametes form? Well, if this organism, and this is very similar to what we're doing with pedigrees, what's the probability now, say, of a gamete having a big Y? Here's the organism that's giving us the gamete. It's a probability of 1/2 that we'll get this big Y. What's the probability that we'll get a big P versus a little p? Well, it's a probability of 1/2 that we'll get the big P instead of the little p. So for this particular gamete here, we would say we need a big Y, probability 1/2, and a big P, probability 1/2, giving this overall gamete a probability of 1/4. The math is exactly the same for the remaining 3 categories. We need a big Y, probability 1/2, and we need a little p, probability 1/2, to give us 1/4. In the next step, what we'll do is we'll assemble a Punnett square using these gametes. So we're doing an F1 times an F1 cross to give us the F2. And here are the gametes that the F1 is producing. So an F1 self is taking these gametes down one side of a Punnett square, as well as these same gametes across the top of a Punnett square. And that's what we'll do in the next little segment. So we have a Punnett square ready to go, and we have the different gametes that are coming from this F1 individual, And those same gametes are on both sides of the Punnett square because this is an F1 self, so an F1 times F1. Now, again, recall that each of these gametes has an equal probability of 1/4. And that's based on the assumption that these two loci are independent of one another. What we're saying by that is we mean the probability of getting one allele at one locus does not influence the probability of getting any particular allele at the other locus. Now, we will see a violation of this quite soon when we start looking at two loci that are physically very close together on the same chromosome. In that particular situation, when you have one allele in a gamete, there is a strong influence on the probability of another gamete because the two are physically coupled together. We'll talk about that more when we get there. At this point, we're simply dealing with loci that are either on separate chromosomes or are far enough apart on the same chromosome that they are assorting independently, that the probability of getting one allele at one locus does not influence the probability at the other locus. Mendel's experiments with the different character traits that he chose all happened to be independently assorting traits. All the different loci that he was using assorted independently. So he didn't observe any violation from this particular pattern, but we will see one soon. What you can then do is go through and fill in the entire Punnett square. And all you're simply doing is combining the different gametes as you go. Each one of these squares has a probability of 1/16. They will also have different phenotypes. This one, for example, will have yellow seeds and purple flowers, as will this one. This one here will also have yellow seeds and purple flowers. And so on. So what I'll do is I'll go ahead and fill out this entire Punnett square, and then we'll come back and look at the different ratios that we'll see. And we'll see it's the same as the ones that we worked out using probabilities in the previous segment.